In this video, we're going to talk about flavin-dependent hydroxylases. You'll recall from the introduction that there are internal and external monooxygenases. And internal monooxygenase, like we said, doesn't typically require a reducing agent. So let's look at an example of that. One example is lactate oxidase. Lactate oxidase is a flavoenzyme that catalyzes the oxidative decarboxylation of lactate to acetate. It's essentially this reaction here. This is lactate. I always remember it because it's reduced pyruvate. And we'll react this with O2. And then our enzyme that has a flavin attached to it. And that will generate an acetate, or acetic acid as I have it drawn here, carbon dioxide, and water. Okay, let's look at some mechanistic studies of this reaction. Okay, so one of the first things they did was they did some labeling studies. So they labeled with oxygen 18. So if you start this reaction with oxygen 18, what they see is the oxygen 18 gets incorporated into the acetate and the water. Remember, this is a monooxygenation, so we're adding one oxygen, typically an OH. That's why these are sometimes called hydroxylases, because they add a hydroxyl group, an OH. Okay, but upon running this reaction with O18 labeled oxygen, they see that O18 being incorporated into the acetic acid or acetate and into the water that's also generated in it. Okay. In the absence of oxygen, they ran the same reaction. This time they had no oxygen in it, and they saw this happen. So there's our lactate. Start off with FMN. It gets converted to FMNH2. This is the reduced form. And they saw pyruvate. It's pyruvic acid or pyruvate. Okay. In this case, in the absence of oxygen, the enzyme behaves like an oxidase. Remember, an oxidase just transfers electrons. There was no oxygen incorporated into this. There was already an oxygen here and here, and they're still there. We didn't add any more oxygens to it. Okay, so it behaved more like an oxidase, not a monooxygenase. So, not monooxygenase. In further studies, what they tried to do was, if they react pyruvate plus oxygen, but this time they did it in the presence of the reduced enzyme, reduced flavoenzyme. And what they saw in this case was as follows. So they started with pyruvate, and they reacted that with reduced FMN, reduced flavoenzyme, and plus oxygen, and they saw EFMN, but they actually saw the correct product. So what this tells us is that pyruvate, this is pyruvate is an intermediate. pyruvate's an intermediate in this reaction. Okay. However, if they react reduced enzyme with oxygen and then pyruvate, a different order than they did before, they saw this. So they started off with reduced, our enzyme, and they treated that with oxygen, and then they added pyruvate. That's our pyruvate. They saw no reaction. Okay. But they did observe the generation of peroxide. The pyruvate was unchanged, but they saw the generation of peroxide. Okay. So therefore, what they concluded was this reaction is much like a flavin-dependent oxidase. Let's look at the overall mechanism for this now. Okay, with this data in mind, they were able to establish the following mechanism. Okay, so I prepared some of the mechanism here for us already. Now, the enzyme, acting like a base, deprotonates the proton on the carbon that's connected to the hydroxyl group of the lactate. That generates this carbanion intermediate. When that reacts with FMN, it generates FMNH2, the reduced form of the enzyme, and oxidizes the lactate to pyruvate. Then when oxygen 18 comes in, it reacts with the FMN. We showed this already. This was shown earlier when we talked about redox reactions. So you can go back and watch the video on that. But it generates this hydroxyflavin intermediate. And the O18 is right here and here. Let's put these 18s in now. Forgot to put them in earlier. Okay. Now there's two possibilities that this peroxyflavin intermediate can undergo. One pathway is this base can deprotonate. We'll call this pathway A here. An enzyme acting like a base can deprotonate and then this attacks to generate this intermediate. Okay, so once again, an enzyme acting like a base deprotonates our flavin peroxide intermediate. That generates an anionic oxygen here. That anionic oxygen attacks this carbonyl carbon and does a nucleophilic addition reaction like we learned in Chem 231 and 232 and generates this intermediate. Now this intermediate collapses. We put these lone pairs in. As follows. Oh, I forgot the base over here. And that generates regenerates FMN and the acetate plus CO2. The other possibility we'll call pathway B, and in this case we generate a peroxide that's bound to the enzyme instead. I'll show you that here. So this, another basic residue on the enzyme, attacks this proton here. This falls into here and then kicks out this peroxide. It's bound to the enzyme. Okay. Now it does a similar reaction. It attacks here to generate this intermediate. I included the oxygen 18s down here. And then this does a similar reaction that we saw earlier. This part here generates the water. It has an oxygen 18 in it. And this becomes our carbonyl with the oxygen 18. Okay, so those are the possible mechanistic pathways for lactate oxidase, an example of a monooxygenase that's an internal monooxygenase and doesn't require an external reducing agent. Okay. What we'll do next is we're going to look at another example of one that requires an external reducing agent.